So the next thing that we want to talk about are the Feynman diagrams of phi to the power 4 theory and phi to the power cubed theory. So let's start with phi to the power 4 theory. And what we want to know is that what are the Feynman diagrams that contribute to, say, order lambda squared in phi to the power 4 theory. So remember, in the phi to the power 4 theory, our vertex looks like this. And in momentum space, our vertex is associated with the factor of I lambda. And therefore, if you're looking at two particles scattering, so we have P1 and P2, two particles scattering to, say, P3, P4, two final particles. So two particles coming in with momentum, for momentum P1 and P2, and then two particles going out with momenta P3 and P4. Now, the question is, what are the diagrams, Feynman diagrams, of this process in phi to the power 4 theory, say up to order lambda squared? So we are only interested in the completely connected diagram because there might be, for example, to order lambda, there might be a diagram like this where P1, the particle P1 goes to particle with P3, momentum P3, and particle with momentum P2 goes to particle with momentum P4, which are all equal momentum, but that we have a loop here. This is an example of a first order diagram, but this is not a completely connected diagram. So we are not going to consider such diagram. In these diagrams, this particle is not really interacting with this particle. There is no interaction. So we don't consider these diagrams as a bona fide scattering process. So the completely connected diagram, the first order, so if you look at order of lambda 0, of course, that is just the identity element, and therefore, again, it means there is no scattering. In order lambda to the power 1, we have two particles coming in. And because we have the phi to the power 4 theory, the two particles going out must be going out from the same vertex. So this is P1, and this is P2, and this is P3, and this is P4. Now, we can write down the amplitude in position space using the position space Feynman rules. But if we do the integrals, then we can Fourier transform to the momentum space Feynman rule. And the momentum space Feynman rule is going to tell us that the amplitude I times m will be nothing but I times lambda. And of course, we have to keep in mind that P1 plus P2 must be equal to P3 plus P4. Now, since we are setting up our experiment, then that means that we know what P1 is and we know what P2 is. And here there are detectors detecting the final particles. Therefore, we know what P3 and P4 are. So everything here is known. So there is no unknown momentum. So according to Feynman rules, there won't be any integral over the unknown momentum. Now, what about the diagrams to order lambda squared? So the diagrams in order lambda squared is that two particles can come in with momentum P1 and momentum P2. Now what can happen is that the two particles can go out like this, and there can be two propagators connecting the two vertices. So this is P3 and P4. Now, the momentum that is flowing here is going to be, say, P1 minus P3. But this momentum can be divided into two parts. Over here, a momentum K can go And here then on this branch, it'll be P1 minus P2 minus K. So that the total momentum going in the internal on the internal lines is P1 minus P3. So this is called a T-channel diagram. So that is one possibility. The other possibility is where P1 and P2, they come in and they meet at the same vertex, and the two internal propagators go like this. So here we have total momentum going through the channel is P1 plus P2, but it can be divided up into different parts like so. And then the outgoing momentum is our P3 and P4. So this is known as the S-channel diagram. And then lastly, P1 can come in, and then from the vertex where, from the same vertex that P1 is coming in, P4 can go out. And then the internal momentum going in that direction is going to be P1 minus P4 minus K, and here there's a plus K. And here we have, say, P3 coming in, and from here we have, sorry, not P2, this should be P2. We have P2, and here we have P3 going out. And this is known as the U-channel diagram. Now, what are the amplitudes for this? So, let's look at the S channel first. So that for the S channel, we have two vertices. That means that we have I lambda squared for the two vertices. And then we have one unknown momentum going in the loop. Therefore, we have to integrate over, say, d4k by 2 pi to the power 4. And then we see that there are two internal propagators, and these propagators are going to give me I I divided by k squared minus m squared plus IE, and then I P1 plus P2 minus k whole squared minus m squared plus epsilon. And then we see that this diagram has a symmetry factor of 2. So we divide by the symmetry factor, so we get half here. So this is going to be the amplitude that is coming from the S diagram. So similarly, for the T diagrams, we will have the same factors here, but these factors will be changed, and I leave those as an exercise for you to do. So up to order lambda squared, our amplitude will be the tree level amplitude, which is I times lambda, and then the second the second order amplitude, which are loop diagrams, will have 3 contribution from the 3 diagrams. So sorry, let me call this T, and then this is U. So this is basically what the amplitude is going to look like up to order lambda squared. Now, one side note, which we won't be covering in this lecture, is that these integrals are actually divergent, and therefore, this probability is actually not well defined because these are infinite quantities. So there is a well-defined structure in quantum field theory known as renormalization, which can deal with this difficulty, but unfortunately, that won't be something we can cover in this course. So this is more of a formal diagram. This makes sense up to the tree level, but in one loop, these guys are not well defined. Next, let me discuss 2-to-2 particle scattering in phi cubed theory. In phi cubed theory, our vertex has three particles going out, and again, we can associate with it I times lambda. And so if we have now two particles going to two particles, there is no diagram at lambda or to the at the order lambda. However, and you can show that easily because if you have two particles coming in and two particles going out, you can't join them, because if we join them, then this is no longer a 5 to the power cubed vertex. This is 5 to the fourth vertex, so this is not allowed. And if you want to join them like this, then we have two vertices, and therefore there are no contribution to the order lambda to order lambda. So the minimum, the leading order terms are from lambda squared. So what are they? Again, like before, we'll have three channels. First, we have the S channel where two particles come in, say P1 and P2, and the internal momentum is now P1 plus P2. Because there is no loop in the internal propagator, we see that there is no integral. There is no integral over unknown momentum. So there's P3 and there's P4. So this is a S channel diagram. So this is number one. And then we also have this thing. Here P1 is coming here, P3 is going there, P2 is coming here, P4 is coming here, and then here we have P1 minus P3. And this is known as the T channel diagram. And lastly, we have P1 coming in, and then from the same vertex, P4 going out, and then so over here we have P2 coming in, and in this direction we have P1 minus P4, and from here we have P3 going out. And this is known as the U channel diagram. And again, like we can just take one of them in random. Let's take the U channel diagram. Then the amplitude from the U channel diagram is going to be just I divided by P1 minus P4 whole squared minus M squared plus IE. And then we are going to have I lambda squared, because we have two vertices, and then we have one propagator. So this is going to be the U channel amplitude, and we can write the amplitude for the other channel. Similarly, see here there is no integral over an undetermined momentum, so these diagrams will not diverge.